So I've been talking to you about how regularization and margin are the same thing. Just to give a brief recap, what we've done in support vector machines is developed a classifier, a linear classifier, or a linear discriminant that has maximum margin, unlike a perceptron, in which the line is can be arbitrarily close to one of the data points in the training dataset. And that gives the support vector machines a much larger error margin. But what I will also be saying is that it also does regularization, which is a property that a classifier has if a small change in its input does not cause a large change in its output, right? And we've seen that regularization can be achieved by minimizing the sum of the square of the weights of the linear discriminant. Because when that is true, let's say if you have a single weight and that is small, then a small change in the input x does not produce a large change in the output. And I've tried to give you a hand waving explanation of why maximizing the margin can be achieved using regularization. Okay, but today what we are going to do is we are going to try to formalize that you or try to present a proof of that to you so that you can have a better understanding of the relationship between margin and and its relationship to regularization. Okay, so we are going to for that uh, we're going to need a mathematical notion of how far away a particular point is from a given line. So if you think about any line, so this doesn't have to do anything with machine learning. So let's say we've got a point over here, and then we've got a line. Then we can define the distance of that line from the point by multiple ways. For example, this can be a line that connects this green point to this line, and that we can use as a distance. Similarly, there can be another line, but typically when we are defining the distance of a point from a line, we use the shortest distance between the two. And there's a very simple proof, I won't be doing that, which shows that the distance of a point from a line, the shortest distance of a point on the line is the projection distance. So what that essentially means is that if I shine light on this point so that the light source is perpendicular to the line itself, then the shadow that that point makes on the line is called the projection of that point on the line. And then we can go ahead and calculate this distance between these 2 points, and that's going to give me the shortest distance of the point from this line. Okay, and we are going to use this information in order to formalize the concept of margin, which is essentially how far is the closest point in the given data set from the linear discriminant that we have made. Remember, we define margin as how much air can you put into a linear discriminant before it touches one of the data points and bursts. So essentially, that can be expressed as the perpendicular distance of the closest point in your data set to the line that you have. So that's why what we are going to do is formalize the concept of margin using this concept of distance of a point from a line. So for this particular line, and I welcome you to draw it on a graph paper or something, and then calculate the perpendicular distance of this point from this line, and it should come out to something like this. But what we want to do is to find a formula that allows us to calculate this distance, and that's what we are going to do. Okay, but before going there, we need to have a couple of steps of this proof. We are trying to prove that regularization and margin are the same, and for that we need a mathematical formulation or a mathematical equation of the distance of a point from the line, the linear discriminant line, which is called the margin. And to do that, we'll be doing two small steps or making two small observations. The first one would be that the line that is expressed by the equation W transpose X plus B is equal to 0. The weight vector, if you consider the W term or the W parameter of that line as a vector, then that vector is always perpendicular to the line itself. That's the first part of the proof. And then what we are going to do is use this fact in order to calculate a formula for the distance itself. Okay, so let's start with this first step, and you can always revisit the video from the end. Once we've reached that, then you can watch it again, and then everything is going to make sense in a very uniform manner. So let's say if you got a linear discriminant, f of x is equal to w transpose x plus b, that is given on your screen. Then what that means is that at any point, let's say if there is a point x1 that is on this line, and you plug that in this equation, then that is going to give you a score of 0 because the point is on the line. So x1 and x2 in this case, because these 2 points are on the line itself, so if you put those in this equation, you are going to get zeros. Okay? And if you subtract this equation, subtract this equation number 1 from this equation number 2, then you can very easily see that we get this expression. Okay, so if you do this, for example, if you change this to minus and you subtract this thing, then these two things cross out, and what you are left with is W transpose multiplied by x2 minus x1 is equal to 0. Now, if you think about this x2 minus x1, then that can be viewed as a vector, exactly this vector. I hope I would have drawn a straighter line, but you get the idea, right? So you've got a vector going from x1 to x2, and that is this vector over here. So that is x2 minus x1, right? Okay. And then we have got a w vector, right? We don't know how to draw the w vector right now, but what we see in this equation that is that the dot product of w vector, which is this vector from the equation or the linear discriminant that we have, the dot product of that with this x2 minus x1 vector is 0. So let me call this the delta vector. So the dot product of W transpose with the delta vector is always 0. And what that means is that W, this weight vector, is always perpendicular to the line itself. So we have got a line on which this delta vector lies. So it's this green line that you see. And what this shows us, or what this gives allows us to observe, is that the weight vector W, wherever it is, it's always going to be perpendicular to the line itself. So if we could draw this weight vector W, then we can very easily draw it as a perpendicular vector to this green line. And that's our first observation, okay? So that's going to help us in formulating the distance, the formula for the distance of a point from a line, okay? So to go on to the next step, we take a point, any point in this feature space xs, and remember what we are interested in is we are interested in finding the distance that we label as r of that point, the perpendicular distance of that point from this green line. And that's what we want to do. And we've already talked about that the shortest distance of this point xs to this line, green line, is going to be the distance of xs from the projection of xs onto this green line. So if we shine some light that is perpendicular to the line itself, this xs is going to then create a shadow, which we call as xp, that is the projection of xs on xp. And that the distance between these 2 points, we are going to use that to define how far away xs is from this given line. Okay, because this point xs is not on the line itself, therefore the distance, therefore the discriminant value for this xs point is not going to be 0. But for the projection point xp, because that point is on the line itself, the value of f of x is equal to W transpose xp plus b is always going to be 0. Okay, we know that from our high school mathematics. Points on the line satisfy the equation of the line. Okay, the next step, what we are going to do is we are going to write this vector xs that is indicated by this blue line from the origin to this point xs. We are going to express that in terms of xp, which is this projection vector, this orange vector that you see on your screen, and this r vector, which is the vector from xp to xs. So I'm going to label that as the r vector. The magnitude of that vector gives us the distance between xs and xp. Simple geometry, right? But we are going to calculate, the first step that we are going to do is we are going to calculate the value of this discriminant for the point xs, and that gives us f xs is equal to W transpose xs plus b, because we already know now, based on this observation on your screen, that we can express xs using the head to tail rule in terms of xp and r vectors. So we can say that xs is equal to xp plus r vector. Okay, so we'll simply put that in. We're going to put that in this equation instead of xs. But we also know that the r vector that you have is perpendicular to the line because it's a perpendicular projection. So that means it's going to be or or parallel or anti-parallel with W vector, which we have proven just in the previous slide, is always perpendicular. So this W vector is always perpendicular to this green line, right? That means the direction of R vector is the same as the direction of the W vector. So we're going to say that R vector is either going to be parallel, which is indicated by these two parallel lines, to this W vector. And what that allows us to do is that we can now go ahead and express R vector in terms of this W vector. Because both of these vectors have the same equation, that means if we say that the magnitude of this R vector is this R without the arrow, then we can write W vector as this R vector as R vector is equal to R multiplied by W unit vector, which indicates the direction of this W vector. And we know that the W unit vector, the unit vector of any vector, is simply the vector itself divided by its norm. Okay, so that's what we are going to do. Okay. So if you're having some trouble understanding these, just revisit or do a Google search on what is the norm of a vector, what is a unit vector. I hope you'll be able to understand it. If there are still questions, we can go ahead and discuss that as well. Okay, so I hope now you would be clear that we can write xs, this point xs, in terms of uh, xp, okay, plus rw unit vector, and that gives us xp plus r into w vector divided by the norm of w. So when we are calculating the decision function value of f of xs, what we do is we put in xs over here and then we replace xs with this bit. Remember, we have already shown this, so we can just put it in there. And because if we expand this bracket, then what we get is WTXP plus this thing plus B. And with some rearrangement, we can say that WTXP plus B plus R times W transpose into W unit vector. And we've already talked about that a unit vector of a vector is the vector itself divided by the norm of that vector. So that's what we've done over here. So this thing is equal to this thing. So we've plugged that in. And once we do that, we already know that because point xp is on the line, therefore W transpose xp plus b is going to be 0. So this thing goes to 0. And we also know that the dot product of a vector with itself is equal to the square of its norm. Okay, and we've shown that in our previous exercises as well. If you're not clear, you can simply think that the first element of the vector is going to be multiplied with the first element of itself, added to the, and that gives rise to the square of the first element, and then you can do that for the second element and so on. So you can very easily see why this would be the case. Okay, and what that means is that this part on the right hand side, what that means is we can write it W transpose W over norm of W is equal to the square of W norm divided by W. And what that means is that we are going to just be left with the norm of W. Okay, so we put that over here, and what that means that we get of relationship f of xs is nothing but r times the norm of W. Okay, and remember, we were interested in doing all this because we wanted to find the value of r, and this allows us to do that. So this is the distance of a point from the line. If you've got a point xs, then you can find the distance, the shortest distance of that point from a given line using this equation, and that's what we have done. Now, what I welcome you to try to do is to calculate the distance of this point 4, 2. So in this case, in this example, xs is equal to 4, 2, and we've got a linear discriminant in which w vector is equal to 1, 2. Okay, so w1 is 1 over here, and then the second part is w2, and the bias value is equal to 3. So what I welcome you to try is that formula that we just derived, and that is f of xs divided by the norm of W. And you can go ahead and calculate this R. If you do that, we know that f of xs, we first need to calculate that. So I'm going to go ahead and do that. And that comes out to be 4 times 1 plus 2 times 2 plus 3. That's the bias term. 4 plus 4 is 8, and that is going to be 11. So f of xs is going to be 11. And the norm of w is going to be uh, the norm 1 squared plus 2 squared under the root. Okay, and that gives me square root of 5. So r is going to be 11 by square root of 5, which comes out to be 4.92. So now what you have is a formula that allows you to calculate how far away a given point is from a line. And you can use that in your real life, everyday life as well. So if someone asks you, let's say, how can you find the distance of a point from a line? It's just this simple formula, right? But what we are going to do is related to machine learning, right? Or what we've been talking about. We know that the distance of a point from a line can be expressed by this equation now, and I welcome you to try out other examples of that so that you understand this bit as well. And if I ask you, what is the point? What point would give no error using the Henge loss function for a linear discriminant, then I hope you would be able to answer that correctly by saying that that point should have a discriminant function score of greater than or equal to 1, right? Because whenever, if you look at the Hinge loss function, whenever that is not the case, we get some loss for that given point, as is indicated by this plot. And we've talked about that when we were developing the Hinge loss function. So if a linear discriminant is at a location where it's not where a given point is not generating an error, then that means f of x value would at least be 1, either on the positive side, or if it can be minus 1 on the other side for a negative class point. So that means the distance of a point from a given line in when we use it in support vector machines is going to be exactly this much. So that's going to be f of xs is replaced by this bit, this one over here, and then we divide it by the norm. And that is the definition of the margin itself. Now r transforms to the margin under this constraint, so that r is the distance of the point from the closest point that has f of x, or the discriminant function value of 1, which does not give us any loss. So if we do that, we can very easily see that the r value is inversely proportional to the norm of w. And that is what we wanted to prove. If you haven't been able to follow any of the mathematics, it's perfectly fine, as long as you understand the conclusion that we are going to give. The distance of a point from a line is interpreted as the margin, right? And that is inversely proportional to the norm of W. That means if I maximize the margin, I can do that by minimizing the norm of W, right? And that's what a support vector machine does. If you go to the formulation of a support vector machine over here that you can see over here, right? We minimize the square of the norm. And the reason we do the square of the norm is because it's easier, because the derivatives are more well formed. That's the only reason. You can actually minimize just the norm of W to achieve the same effect. The conclusion is, the good thing that Vapnik and Shervan-Enkes give is that we should regularize. So a small change in the input should not produce a large change in the output. What we have seen in this proof is that that automatically transforms into maximization of the margin. So I hope with that, I can safely say that this formulation over here, first of all, it does achieve error minimization, so empirical risk minimization, which is this bit over here, the same as the perceptron, but it also achieves, first of all, margin maximization. It maximizes the distance of the line from the points in the training set. So it achieves margin maximization, or it achieves regularization. That is, it keeps the weight value small so that a small change in the input of this linear discriminant does not produce a large change in the output. So I hope this proof helps you understand why margin maximization and regularization are exactly the same. Regularization is a more generic concept, and it transcends from its use in the support vector machines, where it's directly related to margin maximization, to other machine learning models where margin maximization will probably be a bit difficult to interpret. Okay, so regularization can be applied in nonlinear settings, whereas the concept of margin is difficult to visualize when we have nonlinear classifiers or when we have other types of machine learning problems. But at the base of it, both of them are the same. You can achieve margin maximization by doing regularization or by minimizing the norm of the weight vectors. Okay, so that's what I wanted to say, and I hope you have a good understanding of this now. Thank you.